So just for the sake of completeness, I'm Vineet Tiruvadi. I'm an MD PhD at Emory and Georgia Tech.
And I'm Bilal Bari, MD PhD at Johns Hopkins.
And both of us are coming in with a deep background in engineering, about to embark on residency applications, about to embark on residency decisions, life decisions. And we've, I don't know, you and I have been talking gradually over the course of like 6-7 years. And it's interesting to see a convergence now of engineering in medicine in the context of everything that's happening. The research in medicine. So we figured we'd record this and just have our usual chat and see if anything useful comes out of it.
Well, I hope so.
Sorry, so you were saying?
Yeah, well, so the question of mixing how does engineering play into what medicine is? Yeah. And so I think in order to kind of get at that, for me at least, it's useful to think about what engineering is to you.
Yeah.
And so I think engineering as it's traditionally defined is problem solving. Which to me is quite vague, and potentially vague enough to the point of not being that useful. And so I like to kind of think about engineering. Maybe also, I find that it helps to define things in terms of how they contrast to other fields.
Yeah. And
so especially being in medicine where it's so biology focused, then the parts where engineering kind of contrasts to biology. One of the first things that comes to mind is in engineering, one of the first things you learn is you lay bare your assumptions.
Yes.
Right? You say straight out, assuming blah. There's jokes about it, assuming the heart is a cylinder or a sphere, assuming a horse is a cylinder.
Yeah.
But I find that it's quite different from biology. And I'm intentionally casting a wide net here. I'm generalizing. I don't mean to speak to all biologists. But I have the sense that if you go and you give a talk for a biological audience and you say, assuming whatever, I'm going to lay out this problem, there's almost a hush that goes through the crowd, which is like, oh my God, he just made an assumption. Right? And then
you know what they say about assumptions.
Yeah, exactly. Right. And it's just one of these things where I don't think it's explicitly said, but I feel it, right? You feel the sense of people saying, oh, is this really a scientist? Is this really a person you can take seriously? So which I find a bit odd.
Yeah.
Personally, right? Because it's more of a cultural thing. It's not that biology, you don't make assumptions. I feel in biology, oftentimes you don't state the assumptions. And I don't know if you had any particular thoughts about that.
I think one of the most surprising things about the interaction with engineering and medicine is so much that we can go years without necessarily talking about the same subject, and when we come back, we're using the same language. We're talking about things in the same way. We frame assumptions. We frame the problem-solving process in the same way. I agree with everything you said. I think medicine and biology have this potentially bad but understandably necessary habit of, let's assume our measurements did reflect what we thought they reflected, but let's not say that. Like we will proceed kind of pushing the assumptions aside. It's a very much a polite thing to not state your assumptions, and then talk about your methods and talk about your results in a very fixed frame. I would agree. I think the assumptions are very much there. They're just embedded in the citations. They're embedded in this hazier information in who you choose to cite, who you don't choose to cite, how you frame your introduction, how you frame the motivation of isolating these particular two variables. There are assumptions all over there, but there's not an explicit addressing of why did you choose those two variables in the context of why did you not choose these 50 other variables. I don't know if that addressed your question, but yeah. I think that.
I also wonder if, I think just given the competitiveness that exists in science, because to some extent, to state an assumption is to state a limitation, is to state a weakness.
Yeah.
Right. At least in neuroscience, for example, at least the kind of mouse circuit physiology work that I did and the field that I was in for my PhD. People might use a technique, I don't know how familiar you are, two-photon calcium imaging to report some measure of neuronal activity. And if you're in the field long enough, you understand the limitations of that technique. Limitations being, it's not really quite clear what the mapping between the calcium signal and spikes are.
Yeah.
It's a tool that can pick up, it's got good dynamic range for positive changes in spiking, but not negative changes. So you can't really see inhibition that well. And so, but what's interesting is if you kind of mention those weaknesses, and again, I think this is probably due to just the ultra competitive nature of science nowadays.
Yeah.
Is there's a need to defend and say, oh no, these aren't really as weak as you think they are. Right, and oftentimes it's pointing to an absence of evidence, saying, well, we don't really know.
Yeah.
Therefore, we don't have a reason to suspect that things are weak. And so all of that together, I think it's kind of a unique perspective that the engineering training has given me, which is that, you know, as much as you might try to hide it, I do think it enriches your thought and it enriches your ability to kind of, you know, frame a question well, if you're aware of, you know, what limitations you're putting into being able to frame that question, what assumptions you're using. And so that to me is at least one difference that I felt both in medical training and during the PhD that I thought that something that the engineering background gave me that I wasn't quite sure I saw elsewhere.
In a similar vein, and I feel like I was just having this conversation with more physician types, where a lot of it is this there has been a change in the objective function of science. So clearly I'm already coming in with a little bit of the control theory background that I really
please.
But it fits into this conversation, I think, very well. It's engineering is not so much about individual hypotheses. It's about how you achieve hypotheses, how you test hypotheses. It's the process by which you get to where you want to go. And maybe the one thing we share in common is not so much our destination or our vehicle, but the nature of deciding our destination, the nature of deciding our vehicle, how we think about setting up the problem. And this has been in the same way of clearly outlining your assumptions. Draw your system diagram. It's wrong. It's wrong. Get over it. It's wrong. But if you write it down, you don't feel overwhelmed when you figure out that it's wrong. You come in, you put in a new piece, and you say, I think it's related this way. It's an empowering transparency that I think engineering brings, that medicine hasn't always been transparent. It has been this intuitive, maybe more art than science. I don't know what that art versus science thing means, but that's a topic for another day. But I think you said it well. If you lay out the assumptions in a hyper-competitive environment, in an environment where the objective is to maximize something, maximize production, those honest, transparent depictions of limitations and assumptions become weak points in a theory. They become easy weak points in a theory. They become easy avenues of attack to say, that's why your particular hypothesis, which you've staked your career on, because to test your hypothesis, you need to control n-2 variables. That's expensive. That requires a lot of ancillary funding. And so over the course of 10 years, you learn the techniques, specific techniques to control n-2 variables. And at the end of it, you find, that's not a significant result. But you've learned such narrow tools to isolate n-2 variables that you don't know how to shuffle it. And instead of studying A and B, how do you study B and C? Well, that's actually first of all, someone else did a PhD 10 years in that. So they're the ones that are going to get the funding. They're the ones that'll get the postdoc position. So it's best to not maybe put your assumptions. Maybe that's a cynical view. I think that might be a cynical view. I will say that. But there are the kind of openness to assumptions comes from the shared goal. Let's say I'm not interested. I'm not considering myself an expert in combustion engines when I want to build a car or a motorcycle. I want to get somewhere, and I want to get there in a fun way. So if a new engine type comes up or a new engine piece comes up, I'm thinking not, how do I defend myself against this? This engine type that I've been working with, how do I make sure that it is the one that wins this battle that doesn't even exist? Instead, I think, how do I incorporate that into this to improve it? And everyone's kind of building on that to try to get to the cool goal of I want to get there maybe, or I want to get there, or I want to get there the funnest way.
Yeah.
In that kind of, I think, sets the stage of where assumptions and systems diagrams come in, but then the medicine component of it. That I'm very curious about how your experiences in the first 2 years of medical school specifically were maybe enriched, maybe made more difficult by engineering, and then obviously third year, fourth year as well. But we're still in the middle of it in a unique time. So
yeah, I definitely think first 2 years, it's definitely, it's different, because one of the things when I reflect back to my time at Georgia Tech is what made it so difficult is how conceptually driven the entire curriculum was.
Yeah.
Right. It's like just finishing homework wasn't enough, for example, to feel like I really understood that chapter.
Yeah.
Right. And it required like really delving in and saying, okay, well, what are these equations really telling me?
Yeah.
Because, right, even if the objective is just to get a good grade, you can't memorize your way there. Right. You have to know how to take equations, do, kind of the whatever it takes to really wrap your head around it and make sense and say, what is this actually telling me that I might not have wrote, but it's quite clear looking at these equations that I'm able to do X, Y, and Z.
Yeah.
And so I think what was difficult is going into medicine and recognizing, at least with the first 2 years, is that out of necessity, and I do think it's out of necessity, is that has to go out of the window. Yeah. Right? When you join the ranks of medical school to become a doctor, you need to learn a new language, and you need to learn it quick.
Yeah.
And the way to do that is combination of memorization and kind of the enrichment that comes from living in that environment. Yeah. And so for me, I wasn't quite sure if the engineering, maybe you feel different about this, but I wasn't quite sure if it necessarily helped. To me, it felt like a completely orthogonal dimension of my life. The part of me that really, the part of me that quite frankly helped me in research, which is let's try to take noisy, messy data and in this brain try to reduce its dimensions and conceptualize it. That way of thinking didn't really help in medicine, where you have to know everything. You have to know every exception. You have to know, side effects. You have to know, the associations between different conditions, so on and so on. Yeah. So yeah, I don't know. I feel like early on in training felt like a limitation. Not a limitation. It felt like it hadn't necessarily helped.
Right. Right. I feel similarly. I think I was a little bit more reluctant than you to change my perspective on that. So the best example I always go to is machine learning and regression fitting, for example. We were being, medicine is a living field. It's constantly changing. The information that they're giving and they're testing will change in a year. Mm-hmm. So part of me, and keep in mind this was 7 years ago and my attitude has matured. 8 years ago, I thought to myself, and I paid dearly for it, but I said, let me find the common theme here. Let me find the underlying principles here. And I will do the tests based off of those underlying principles. There aren't many underlying principles that we know of yet in medicine. So naturally that was reflected in missing the questions that were a little bit more specific about things, but it was definitely a struggle. Orthogonal would be putting it nicely. I think they are opposite. I think one type really, really stresses the thought process of, I will never forget my physics classes, right, in undergrad, where they put a slide up and they say, this test is about this one slide, and that slide is F equals MA. They're not wrong, but that instills in you this suspicion, a good suspicion, but when someone says, just look at this slide, everything that you need to know is on the slide, my thought process isn't, I believe that, let me just look at that slide and I'm good to go. My thought process is, oh, you're about to really test deep understanding. So I need to play around with this material on this one slide. I need to play around with it, see how it fits in with each other. And it takes quite a bit of time to realize, wait a minute, a lot of pieces of medicine don't necessarily fit in together yet. And there is no common theme. There is no underlying pathophysiology principles. That being said, there has been major progress in the last 20, 30 years. So I felt like maybe we trained at a really interesting cusp where we were starting to learn these systems-based, in the engineering sense, systems-based principles of how each organ system really interacted. Systems-based, not in the anatomical sense, but systems-based in your body has an exhaust system. Your body has an energy system. Your body has a signaling system. Your body has a control system. Your body has a motor system. And maybe our curricula go through them in an anatomical way, but we were starting to gain basic principles of, no, the immune system is everywhere. It's not just the anatomical regions that the immune cells live in, but the immune system comes in and regulates everything. That is a system, just like the cooling system in your car is a system. So it was a weird, I think I paid a price in the preclinical, but the positives of it came back in the PhD, where it was that engineering style thinking, but I had already tried to see the heart, the lungs, the immune system as one system already. So, so just kind of leveraging these different domains to try to understand the guiding underlying principles brought me ultimately to dynamics and control, which I had some foundation in, and took me a while to realize, wait a minute, there's a way to frame everything in that context and put a black box for the principles that we don't necessarily understand. And there's a transfer function there between inputs and outputs that is unknown. So in classic med school learning mode, that's a predictive model, right? I don't know why these inputs are going to these outputs, but I know for that test, I need to explicitly map these inputs to the outputs to get a high accuracy on my test. So yeah, so I think I think I agree a lot with the challenges there. I am curious, we don't necessarily have to move on, but then third year changes the game, doesn't it?
Well, I want to, right, one of the things you brought up, and I like this analogy of where you brought up the idea of regression, or at least you get broader, machine learning.
Yeah.
And I want to tie that to what you said earlier, which is maybe the engineering way of thinking and this memorization way of thinking are actually opposite of one another.
Yeah.
And I think you have a good point there. Conversation I had with a friend of mine a long time ago, where we were trying to figure out if there's something adaptive about forgetting.
Yes.
Right. And in medical school, you don't want to forget anything, right? And if you forget, you feel weak. You feel like I haven't studied enough. I'm not going to do well enough. I'm not going to look smart enough.
Yeah.
But what you learn in machine learning, and I wonder if you can think of regularization as right. Is this like, in a way, you're trying in some way to forget pieces of data, because what you're trying to do is to essentially see past the noise and figure out what is the true generative model.
Overfitting, yeah. You want to avoid overfitting in your training set so that on the testing set, third year, fourth year of med school, you're able to achieve a decent accuracy versus, but that does come at the cost of accuracy in the training set. Yeah. Regularization was exactly what I was going for. I don't think I finished that thought, but yeah.
Yeah. And so, it is interesting. It's almost, I mean, this is now a testable hypothesis, right?
Agreed. So actually, I encountered this paper early in my PhD, and it completely transformed the way I thought. It was the paper from Aaron Batista, Byron Yu. They're up at Pittsburgh. I think it's called Neural Constraints on Learning. It's 2013, I believe. Sadler et al. Sadtler. It was in Nature, and they did this beautiful experiment. I thought it was a beautiful experiment where they had two non-human primates. They had BCIs in motor cortex, BCIs being brain-computer interfaces for anyone who's potentially watching. These BCIs are little electrodes that go into part of your brain that's associated with movement. It's one of the closest signals to your muscles that tells your muscles to move. So if you're able to listen in on that part of the brain up here in motor cortex and listen in just the right way, you might actually be able to interpret movements and predict what movements the non-human primate, or in some cases the human, wanted to make. So they did this beautiful experiment where they let the BCI learn the combination of electrodes and the combination of weights needed to control a cursor on a 2D screen well. Established work. A lot of really good work from Shenoy Lab out at Stanford. I think Batista did a postdoc with Shenoy. So really solid work. But what they then did was they tested the monkey's ability to relearn in the context of the frame that they already learned. So how they did this was they had 100 channels in their BCI. They learned linear weights between those channels and the ultimate two-dimensional cursor movement. They learned the weights, and then they actually perturbed the weights in two ways. They perturbed them in manifold. So those coefficients, they trace a line in this high-dimensional, 100-dimensional space. They did things like, let's say, just weakened all the weights. All of them, just divided them by 2. The monkey was able to relearn. The monkey was like, okay, I guess within reason, I can make do. I can just double the activity to get to the cursor to where I want. The monkey was able to relearn, and the BCI new coefficients were able to achieve the same performance. But then what they did was they moved it out of manifold. And there's a lot of different directions to move it out of manifold. Their paper goes over how they decided to move it out of manifold in some beautiful way. But when they move it out of manifold, the monkey's performance plummets and stays down. And then when they switch the coefficients back to what the monkey originally learned, it went right back to where it was before. Right back to where it was before. Versus when they did in manifold changes, the performance decreased, they were able to learn again. And then when they changed it back to the old way, it decreased and they were able to learn again. They had this beautiful picture that changed the way I think about learning, maybe in a positive way, maybe in a negative way. But what those coefficient changes could look like is they're adapting to this connections in your neurons, right? Your neurons are connected to neurons in a very specific structure. If you move things in manifold, all you're doing is you're maintaining the correlations in those neurons. You're just weighing them. You're just linearly weighing them with a scalar. If you start going out of manifold, you're now expecting there to be connections between neurons that don't have connections. Two neurons that were firing together now are expected to not fire opposite each other to achieve the same output goal. That doesn't happen in a day. That takes time, if it's even possible. When we learn, when medical school puts a virtue to learning details, what that means is when I hear A, I say B. Right? That means that the part of my brain that does A and the part of my brain that does B, their link is strengthened. It makes it by definition, hypothesis, it by definition makes it so that you cannot do, that network cannot do certain things anymore. And one thing that it cannot do is decouple A and B. Because you learned, like by definition, you learned A becomes B. So when I get asked a question by my attending, I give the answer. So when I'm like, well, what if B but slightly different? That's not a thing that this network can support. But that's the kind of thing we are expected to do in PhD land, in grad school land. What if this isn't the case? Answering, well, I never did that experiment, or it's not in the book, is not a valid answer. So I do strongly believe our brains are networks, and so much lives in the connectivity that when you support one type of learning, you're actively discouraging another type of learning. You can't have a network that quickly goes to its destination and is good at exploring at the same time. Exploring. That's a hypothesis, but it does start, I think, hopefully inspiring questions as to what values should we be prioritizing in medical education, when it becomes less about memorizing things within the context of up to date, in the context of clinical decision helpers, and more about navigating and exploring a space to try to find novel solutions.